Okay, so before we get into review here, just a couple of notes on my schedule for the rest of the week. Of course, I've got assignments 3 and 4 to get back, so assignment 4 is coming in today, and I'm sure there'll be a couple coming in a bit later on in the day as well. So over kind of today and tomorrow, mostly I'll be marking to try and get those done, and I'm hoping I'll get them done by the end of Wednesday, so that they're available with lots of time for studying on the weekend. I will also be getting the practice final exam up. I haven't got that up yet, but I'm hoping to get that up in the next couple of days as well. With the last assignment, the Revit one that you guys are working on in the lab, of course we got the full 3-hour lab period available for that this week. And I'm anticipating that most of you will probably only need half of that time in order to finish up based on how far you got last week. So that, because the Revit is not anything that's going to be on the final exam, I'm not going to worry about getting that marked this week, and I'll mark that next week, and I'll have some comments available after the exam on that. Final exam and assignments 3 and 4, hopefully by Wednesday-ish, I'll have all of that done. Okay, so let's take a quick look at the review. So we started with steel. Now, the first thing we looked at with steel was looking at plastic bending. We looked at defining that function called a shape factor. And it allowed us to identify that there is difference in plastic behavior versus elastic behavior. And from a design perspective, our MR that we were looking at, we have two formulas, one based on class 1 and 2, and one based on class 3. And there is a class 4, which we briefly alluded to, which is mostly based off of the S136, which is the light gauge steel construction. Of course, our steel code that we're using is S16, so there's a different code involved for light gauge steel construction, which is the class 4. Right, so the big difference between these two is whether you use elastic design principles or elastic design principles, elastic or plastic design principles. For the most part, while we went through the derivation of the method and the equations, it's a matter of looking up MR directly off of the blue pages. Right? Now we also looked at MR prime. Right? This is our moment resistance when we're talking about a laterally unsupported length in the compression zone where there could be localized buckling that happens. Right? So here now is a reduction factor, and I won't write out the formula for this because it's a fairly long, complex formula. It takes into account a bending, well, there's a bending component, there's a twisting, and then there's a distortion component as well. Right? So the formula is quite complex, and it takes a number of factors into account. What we have to recognize is if I have a scenario for which there is unsupported bending, I need to make sure that my moment resistance is reduced based on that unsupported length. And the typical examples that we looked at are things like a Gerber-Girder system, where I've got negative moment at the supports and positive moments in the main span. So my positive moment, I'm going to just be calculating MR, but my negative moment, I'm going to be looking at this MR prime. Now, even with MR, we could still end up, if I've got what appears to be full lateral support, I need to look at what the spacing of that support is. Right? If I've got joists that sit on top of beams and the joist spacing is 3 meters apart, there could be a slight reduction factor. Right? And when we're looking at our tables here, our MR portion of the blue tables are ordered such that if I just go to the bold sections only, the top of each category, I will get the most efficient section. Right? They are ordered so that within each category, the one at the top is the lightest section with the highest moment resistance. Now, when I'm looking at my MR prime, I don't have the order of the table working to my advantage there. It becomes much harder to figure out what the optimal size is going to be. What I end up having to do is look at several different sizes and compare the weights and try and come up with the one that's the lightest. So it's a little bit more tricky when we're dealing with our MR prime. Now we also looked at, for steel, several different methods for deflection. We looked at using our equations, like our 5W to the 4th over 384I equation. But we also looked at a BD-CD formula, where BD and CD are pulled off of a table and a graph. That one in particular is really useful if I'm dealing with statically indeterminate or with weird loading patterns. And then there's also our beam loading tables, where there's an approximate deflection based on 240 MPa. So we calculate what the actual stress is and calculate our deflection based on that approximate deflection multiplied by the ratio of actual stress to that 240 MPa. Right, so several different methods we looked at for deflection. So just like we had with our wood beams, we have moment resistance, shear resistance, and deflection requirement. So the last thing that we're looking at here for steel is our shear resistance. Now our shear resistance, we're just looking at the web only. So it's area of the web times our allowable stress. And just like with our moment resistance, there's a stress as part of the calculation as well. We're looking at 350 MPa is the Canadian value, but our American steel is 345 MPa. So since a lot of the steel that we get in Canada is based off or imported from the States, if you're ever doing any calculation by hand, you're going to use 345 MPa because we don't know necessarily whether it's from a Canadian supplier or an American supplier. So 345 is on the safe side. The one exception to that is if I'm using HSS. With an HSS section, we can basically guarantee that we are going to get Canadian produced sections. So if I'm doing an HSS section by hand, I will actually use 350 MPa for that. But for anything else, I'll use 345 MPa. Now, other than the fact that our shear resistance is based off of the web, what we notice with steel beams is that the shear hardly ever governs. If I have a simply supported beam with UDL, shear is not the governing factor. The only time that shear is going to govern is, well, there's kind of three scenarios that we're looking at. One is if I happen to have a really short beam. The second one is if I have a point load applied very close to the support, which creates a high shear but not very much moment. And the third one is if I'm cutting holes in the beam. Now typically at the end of the beam where we have our highest shear, we might have a bolted connection, so there'll be a couple of holes drilled in there to put some bolts in. But typically that's not a huge amount of reduction in area, and it's not something that we normally worry about when we're doing our basic beam design. It might be something that during the detailed connection design stage, that the detailed connection designer might take a closer look at that and say, oh, well, I've got 5 bolts in here, that's a significant chunk of area, let's calculate the shear, and if necessary, they might have to either distribute it instead of 5 bolts all in a row, put it in as 6 bolts, but in 2 rows, right? So that the amount that you're reducing from one particular shear plane is minimized, right? Or in some cases, we might actually choose a different beam size where the thickness of the web is slightly bigger to give us a bit more shear resistance. But normally, we're not worrying about that as we go through our calculations, right? So we have our moment resistance, shear resistance, and then 3 different methods for deflection. Next, we are looking at columns. And for the most part, we're looking at the green pages here. Green, we mentioned here for beams, blue pages. And so in our blue pages, there's 2 sections of blue pages. The first section gives our beam design tables and the beam load tables. And the second set of blue pages is the composite tables. It still falls under the classification of bending. Our columns, these are our green pages. And our columns are based on weak direction bending. So in most cases, if we want to design a column, it's just a matter of finding an appropriate KL value, going to the tables, reading across the appropriate KL, and we come up with a number of different column sizes that will work. Here, like doing our MR prime calculation, there are several that are going to work, and I need to compare the mass in order to come up with the most efficient section. So the tables aren't necessarily organized for coming up with that most efficient section. Again, you're looking at several potential ones that work and then trying to find out whichever one happens to be the lightest. Now, in some cases, if you've got a non-symmetric section or a non-symmetric loading or a non-symmetric support conditions, we might find a scenario where the buckling is actually going to be in the X direction rather than in the Y direction, or strong axis instead of weak axis. And here, what we're doing is we're calculating a KL over R. Right, so we'll do a KL over R in the X, over R, versus a KL over R in the Y, right? And it's the larger KL over R which governs. Now, the problem that we have here is, in order to be able to do that determination, I need to first of all have R, right? And R is based on our column size, right? So typically what we do is even if we have something that buckles in the X direction, what we're going to do is design based on the weak direction and then check in the X direction. And if it doesn't work in the X direction, then increase the column size. Now in section 6, so these are white pages towards the back of the Steel Design Handbook, where you're looking at the properties for individual column sections, you'll notice that the grouping there is around like radius of gyration. So if you're within that grouping, you don't have to go back and recalculate KL over R because the R values don't change very much. Right? They do change a little bit, but they don't change by much. Right? So that means that I can design based on the weak direction, check it in the X, and if it doesn't work, I go to that section 6 and I increase the column size within that grouping, and I don't have to go back and recheck everything. Another approach is by calculating our KL over R, and so when we're checking our X direction, we're using a KL over R tables. Right? So with KL over R tables, we come up with a CR over A. I multiply by the area, and I come up with a compressive resistance. So that's how we're going and checking that in the X direction. Right? So we're always going to start with weak direction buckling, just so that we can come up with that initial size. Next, we were looking at connections. I'll mention here as well in columns. We did actually look at, for the most part with columns, we assume pin-pin connections so that we can just design it like an axial only. But we did also, when we were dealing with columns, take a look at scenarios where there was bending as well. Right? So typically what we call a beam column. Right? So we call it a beam column because it has aspects of a beam, the bending, plus aspects of a column, the axial force. There is actually, in the wood design tables, there are a separate set of tables for beam columns. Again, these are elements that have both bending and axial. They could actually be beams, or they could actually be columns, but usually they're columns with bending is the kind of scenario that we're looking at. So if we've got that kind of scenario, it's much more rare in steel to have that kind of configuration, because typically our connections are such that we do consider them to be pinned top and bottom. So if we do happen to have bending, then we have some separate combined stress calculations that we need to go through. Right? And again, they're just based on P over A plus or minus M over S, right, in the two basic directions. But rather than calculate it in terms of stress or force, like we talked about in our strength materials course, what we're doing here is coming up with a force divided by resistance. Right? So there'll be a PF divided by a PC, or a PR rather. And then we add to that, so that number should be less than 1 by itself. And then we add in a bending, and MF divided by an MR, right? We can do that in both the X and the Y direction. And we add both of those together, and if this whole thing is less than 1, then we have something that works. Now there were some modification factors that we put on there, so rather than just MF over MR, depending upon whether it's a class 1, class 2, class 3 system, there's a slight difference in the equation that's used. We have a U1 term out in front. Depending on the equation, there might be a beta term out in front that needs to be calculated. And we also looked at our what's called in the Steel Design Handbook lateral stability, which is our P delta check. So if we do have a scenario where the P delta effect could come into play, there's a multiplication factor coming from our U2. So that's applied to our moments. Right? So that's all part of the columns as well, but they're less common. They're more complicated, but they're less common than our standard pin-pin scenario, which is just the green pages and look up the column size directly. Now, with our connections in the yellow pages, we looked at bolted connections, and we looked at welds. And we just did a quick and dirty look at the connections. It is possible to have an entire course just on connections. Right, so we did not really get into this in much detail. Again, there are specialty connection designers that will work with the steel fabricators and come up with a set of shop drawings. They go through a little bit more detail. So things like bolt groups and bolt group tear-outs we didn't talk about in any great detail. So for the most part, we're looking at with bolted connections. Oh.
Sorry.
So with bolted connection, we're looking at a shear resistance. So we're just looking at the number of shear planes, right? So we looked at single shear versus double shear. And each bolt is going to have a particular shear resistance. So there were several different grades of bolts, an A325 or an A490. And we talked about threads intercepted or threads excluded within that shear plane, but it's a basic shear connection. Now, as part of the design though, if we've got the bolt that has a particular shear resistance, that bolt in turn exerts a bearing stress on the steel. So there's a bearing stress calculation as part of that, right? So you're checking not just that the bolt can handle it, but that the steel that it's connecting to can also handle it as well. And then lastly, we looked at slip critical. Now, slip critical with our bolts is a little bit different because with slip critical, we technically define this as a serviceability limit state rather than an ultimate limit state. So what that means is if it does happen to slip, then the building's not working as intended, but it's not a collapse mechanism. Whereas with the previous calculations, the bolt shear, right, if I exceed the allowable shear stress in the bolt and the bolt just snaps in half, right, we do potentially have a collapse mechanism, right, and potentially that could impact people's lives. So as a result, we have a significant safety factor involved with it. Whereas with a slip, right, if we do happen to have a slip, and this again is a friction factor that we're looking at between the two pieces of metal based on the amount of tension that the bolt is tightened up on. If there is a slip, then eventually we'll get to a point where the bolt will become in shear and it will exert a bearing stress. So a slip critical connection still has to have a shear check and a bearing check as well, right? And that's the strength part where we have factored loads and factors of safety, our 1.25 dead, 1.5 live, and our 5 factors and so on. Again, notice with our connection details, as we apply our factors of safety, the 5 factor is much less than what we're looking at for other design parameters. So for our columns or our beam designs, moments, shear, axial load, there typically we're using a 5 factor 0.9 for steel, whereas when we get to connections, bolts, we're using 0.8. The idea here is that we want to force any potential failure to be away from the brittle failure mechanisms. Right? If there is going to be a collapse, what we want to see is excessive deflection first, so that hopefully somebody will notice it and say, this doesn't look right, let's do an investigation. If we put a higher factor of safety on our connection details, then what that means is theoretically they can handle more load, so that means that we're going to go into plastic bending before we get to failure in our connection details. Now with our welds, we were just basically looking at fillet welds and butt welds, a variety of different types of butt welds that we were looking at. And like we had with our bolts, there is, with the bolts we had the shear of the bolt and then a bearing of the bolt back on the steel plate. With the welds, we've got a check of the weld metal, and then we've got a check of the base metal. And again, for the most part, it's stress times area. Right? It's a sigma equals P over A type calculation with a factor of safety thrown in. Now, if you take a look at your welds, the 5 factor is reduced yet again, so we're looking at 0.67. This is to account for a higher variability in welds. We looked at with a fillet weld, perpendicular versus parallel, and a slight little modification factor on the formula. And then there is actually a part of the formula that deals with both perpendicular and parallel at the same time. We tend to neglect that as much as possible. It just adds an extra little, an extra term in the equation, but in most cases it doesn't really give us anything significant. Now the last thing that we looked at on steel was our composite decks. We also looked at a few other things like base plates, that could fit in with the connection details as well. So base plates, we looked at coming up with the size of the plate, right, making sure we're not exceeding the allowable bearing stress of the concrete. So that's the physical size. And then we had the thickness of the plate, and then we talked about the bolt prying action. And if we make the plate thick enough, right? If there is tension and if the plate is trying to pry up on the bolt, if I make the plate thick enough, then we don't have to worry about the prying issue. And that's usually how most people deal with it. Now with our composite deck, the reason we talk about composite deck in here is because this is the one real case that we looked at where we actually take into account construction loads separately than service loads. Right? So pretty much everything that we've looked at, the wood design and most of what we looked at in steel and even in concrete as well, what we're focusing on is we have this design value that we want to be able to match or meet. And it's based on how much load we expect on the structure when the structure is in use. Now here with our composite deck system, we're looking at different loading patterns for different phases of construction. Right, so we looked at the first stage, so the columns have been erected, and we have some beams that go between the columns, and those beams, we're designing like a simply supported connection based on our full service load. Right, that hasn't really changed. It's these beams that span between the beams that are kind of running like joists. Right, so there's smaller beams that span between the main beams. So when we're looking at the design of those, we're looking at a construction load case where we've got a steel deck and we're laying it on top. And we have a couple of workers that are on top in order to be able to weld through and connect that steel deck onto the beam. So since that steel deck is not physically connected to the beam yet, that means we have no lateral support on the top flange. So we have to design our beam to be able to resist that construction load case with full length as the unsupported length. As soon as that steel deck is applied, then the steel deck provides lateral support to the top flange. So when we pour the concrete on top of there, we've got to get workers up there leveling out and smoothing up the concrete, and the concrete is well wet, so it's not doing anything yet. So our construction load case is those beams have to be designed to be able to handle that load, but now we can make use of full lateral support. And then the last stage is when the concrete is set up sufficiently and we have full composite action. And here for our full composite action, now we're looking at the full design load case that we're considering. So all the dead load and all the live load for our service condition and that 3 case. The big issue with our composite deck is that our selection tables are based on their trial selection tables. They make some assumptions in terms of where the neutral axis is. So after we go through and come up with a size from those trial selection tables, we need to do a set of detailed calculations. So we do a detailed bending calculation based on plastic design principles, and then we do a detailed deflection check based on elastic design principles. So the big part is calculating where the location of the neutral axis is and calculating our moment resistance of that plastic state from first principles. So force times distance plus force times distance. So it's a little bit time consuming, but it does give us an advantage. All right, so that kind of concluded what we looked at with our steel. And then we took a look at concrete. In concrete, we'll go through a little bit quicker because that's, of course, more recent. So we looked at beams and slabs. And for the most part, we're looking at moment resistance. So moment resistance has to be, of course, greater than factored moment. And we've got our KR tables that are used to come up with this. Right? So we set MR equal to MF. We solve for KR. We use this to come up with a reinforcing ratio. And then we use this to come up with an area of steel. And then we come up with a bar configuration from that. Now our slabs, for the most part, follows the same principle. The difference is instead of putting a finite number of bars, the bar is done in terms of spacing over a 1 meter wide strip. Right? So we do spacing instead of a finite number of bars. We also had our shear resistance. Now for beams, we looked at BF was BR was BC plus BS. There was a shear resistance that the concrete can handle, and what the concrete can't handle, we make up for by putting in stirrups. And our stirrups, we based on number of vertical bars in the sections. So considering that most of the time we're going to use 10 M bars, what that means is that the area of steel used for our shear is always going to be multiples of 200. So 200 is one full closed stirrup, so with 2 bars going up vertically. If I put in one hoop, I've got 200, 2 hoops, 400, 3 hoops, 600, and so on. So it's always multiples of 200. Now for both of these calculations, MR and VR, we had a number of design checks that we needed to go through. So we had a minimum amount of steel, we had spacing requirements, we had a crack control parameter, we had a 1.2 times a cracking moment check. Minimum area of steel, slightly different formula between beams and slabs, but there are a number of checks that need to be gone through. Now, when we did our beams and slabs, one thing we did not do was deflection calculations. Right? Deflection calculations can get quite complex. So what we did here is we said, as long as we meet some certain minimum thickness, then I don't have to do deflection calculations. And then lastly, we looked at columns. In columns, we had slender versus non-slender. And this calculation was based on a KL over R calculation. So then we have an approximate method of dealing with the radius of gyration, which is really nice. It avoids that issue we had with the steel section, where you've got to design something before you've got an R, before you can do your KL over R. So here we can come up with an R value based on an approximate formula. And I can use that to go through and determine whether or not, based on another KL over R formula, whether our column is considered slender or not. If it's not considered slender, I'm just going to go to my interaction diagrams, come up with the shape of the curve, and I'm going to see if my point is inside, in which case it works, or outside, in which case it doesn't work. If it's outside, I increase the amount of rebar. With the slender columns, we have the additional wrinkle of now taking into account P delta effect. So with the P delta effect, instead of calculating based on our MF, right, the moment that's on the column, we now have an MC that we need to calculate. So our MC is our amplified moment, much like the U2 factor was for steel. So there we go through and calculate an EI value, right? We need to know EI in order to calculate the Euler buckling, critical buckling stress, and that becomes part of our formula for our amplified moment. And what that means is when we go through our calculation, if we come up with a guess and we come up with a scenario where I've got an interaction curve, that looks like this, and I come up with a point out here, point out here. Right, so outside the curve so it doesn't work. So your first thought is, okay, let's put more reinforcing in. Well, if I put more reinforcing in, what happens is that the Euler buckling load goes down, so this point will actually go that way. At the same time, because you're putting in more steel, the curve will shift that way. So what you end up with is if you're outside the curve, I'm going to take a look at the reinforcing ratio for an equivalent curve that will be out here somewhere, and the reinforcing ratio for this one, and I'm going to take something in about the middle. Right? Not necessarily exactly the middle, you don't have to do an interpolation or anything in there, but you come up with a configuration that looks like it might work, and you try it again. And if it doesn't work, then you might have to iterate one more time, but you shouldn't have to do any more than 2 iterations on this. So slight little difference in the slender in that this point will move. It only moves in the horizontal. It doesn't move up and down. Like the P over AG remains the same. And then lastly, we just finished off with our foundations today. Again, it's much like what we looked at with our beams and slabs. The only thing that we added in today was the two-way shear effect with a separate shear calculation. So that's our quick and dirty review. Yes?
Do you have any idea of how much will be pre-midterm versus post-midterm?
Probably 75% post-midterm. Right, so there'll be a couple of steel questions and a couple of probably more like four concrete questions and 2 steel questions, somewhere in that neighborhood. Yeah.
Are there going to be short answer questions?
There'll probably be a few short answer questions. So maybe 20% of the exam. And these are the short questions, if there are any, and I'm not 100% sure yet, but are going to be the sort of things where you've got a really quick calculation to do, like determine the maximum KL over R for which slenderness effects can be neglected for a column, right? Just do that one calculation and you're done, right? Not rather than the full design question, which takes like half an hour, right? So relatively short calculations would be those kind of short answer part. Okay, yep.
So you're not expecting any of those to be like verbal
questions, like why is this?
Why, there might be one or two of those, but yeah, we'll try and keep them to the minimum. Yeah.
How complicated of a composite deck question are we expected to do?